Okay, I think we'll move on to the next group. This is the open source ultra low cost sensor array group. This was advised by Dr. Luc Rumbaugh and myself, Mark Ruber, in France, which this whole group studied for their first semester. And we'll let them take it away.
Thank you, Dr. Ruber. So my name is Jacob Eisenhart, and I was the team lead for the open source ultra low cost sensor array team. We'd like to give a special thank you to Dr. Ruber and Dr. Rumbaugh, who helped us throughout this year on this project. So on the bottom left there, you can see our team. Starting going from left to right, you have Alex Ferland, who is our lead programmer, Tony LaRosa, who is in charge of prototype design and production, Michael Kishler is in charge of testing and our budget, Michael Moldovan, who assisted in our programming and testing, and then myself. So as Dr. Ruber said, our team was located in France, specifically in Nantes, and we were partnered with a grande école called Honoris, which is the equivalent of like a graduate school here in the United States. And they're an agricultural engineering and food science school. So we were partnered with their food science department in creating a sensor array to calibrate tuttle ovens and ensure proper temperature of those ovens and also proper temperature of the food products that go through those tunnel ovens. This is really important in France. Freshness and quality is of the utmost importance there. So they want to make sure that their ovens are operating correctly and also that their food products are cooked to a high quality. So as you can see on the left here, this is just a diagram of what our sensor array looks like. So first you have a DAC unit, which comprised of a microcontroller, an Arduino in our case, and those are connected to sensors. And those sensors will read in the temperature, heat flux, humidity from the temperature or from the tunnel oven and save those data values into our DAC unit. And then we have a thermal protective barrier outside of the DAC unit to protect it from the heat of the oven, because these tunnel ovens can reach anywhere between 200 and 250 degrees Celsius. So we want to make sure that we keep our components cool so that they function properly throughout the duration that they're in the tunnel oven. On the right there, you can see a commercial product that is out on the market as it runs through the tunnel oven. And they're able to calibrate these ovens right on the production line as they're producing whatever product they are. So they're able to either record the temperature of the oven itself or of a food product. So here it might be a little bit hard to tell, but height is the utmost importance here. It's a little bit of a wider array, but it's very thin. So for our project, we want to make sure that we make it as thin as possible. Next slide, please. Okay, so this is not the first year of this project. It was actually started back in 2016 with the initial creation of the concept. And then the year after that, they designed and created the high temperature test bed. So that's the test bed that we actually used on our prototype that we have at the European Study Center in France. Last fall, they worked on the further development of the DAC unit using various Arduinos, and then also implemented some larger arrays to use more thermocouples. They also were able to use some simple on-off control to turn their DAC unit on and off. So our task this year was to create a family of LCA prototypes that varied in size and functionality and also reduce the footprint. As I said before, height is the most important for us. So our team created 4 objectives from our specifications that we were given by Honoris. So first, we wanted to develop a 6 to 8 thermocouple microcontroller-based sensor array. Second, we wanted to test that sensor array to make sure that it would operate in the oven inside of our thermal barrier and not get too hot. Third, we wanted to shrink that array to meet our dimensional specifications. Height is the most important, but we did have some width and length requirements as well. Last, we wanted to make sure that our sensor array was easy for the user to analyze and collect their data and export that to a computer. So in this presentation, after myself, Tony LaRosa will be speaking about the proof of concept and prototypes 1 and 2. Then Alex Ferland will be talking about the software that we use to control our proof of concept and our prototypes. Then Michael Moldovan and Michael Kishler will be talking about testing of our various parts of our project. Michael Moldovan will be talking about some PC software that he developed to interface with the Arduino. Then Michael Kishler will be talking about the budget of our project. And finally, Tony LaRosa will be speaking about our final prototype design and also giving some of our thoughts and what we learned throughout this process. So I'm going to turn it over to Tony now to talk about the proof of concept and prototypes 1 and 2.
So to start off this design process, in the history of the project, they've been working on choosing different microcontrollers, choosing on different apparatuses, breadboarding types, circuitry types, and amplifiers for the thermocouples. And so some things that we were going to focus on were obviously the size requirement, as Jake had said, an efficient layout so that we can keep it as small as possible, easy to modify because this is a prototype and we want to be able to change it based on our customers' needs, external controls, so there's no open circuitry, multiple thermocouples so that the client can choose and measure data points as he or she wants, and to make it very, very cost efficient. So as you can see in the bottom right, there is an industry standard Digitron ThermoPro 2, which is what our customer currently uses, and it is enclosed in its thermal barriers, which you can see is that steel and ceramic. And so this is kind of the height and standard that we're going to compete with, and these run around 10,000, so we're trying to come in well under that. So most of our prototypes were loose wire prototypes. As you can see on the left, this was early staging testing prototypes. And then as we get into our first prototype, more of a tight wire design, more of a horizontal spread, still using a breadboard and an internal power supply. But now we have some external switches and indicator LEDs for you to be able to store data, turn it on and off, and export that data to a computer via a USB connection with the Arduino Mega. As you can see a closer picture here, we are 14 centimeters across, and keeping our height minimum. This prototype measures in 6 centimeters tall, which is in retrospect about the length of a thumb. So prototype 2, our first prototype was pretty spacious, and so we wanted to make that very compact. So we made a smaller footprint. This one is about 10 centimeters across with a slightly decreased height. This one is 5 centimeters tall. Components utilized a vertical orientation, as you can see in the bottom left. And then we swapped out our microcontroller for a smaller one and then had to upgrade its memory with an external SD card. We also created like a robust barrel jack connection system for our thermocouples so that they would be able to have a longer lifespan and suit our clients' needs. And this comes in at about $170. As you can get a closer look, we have a single switch and 2 indicator LEDs. We have the micro SD card reader, which fits nicely in the center. Our 4 barrel jack connections for 4 thermocouples on this prototype. We also have still internal battery and our Arduino Micro. And as I said before, 10 centimeters across. And so Alex Ferland now will start to talk about the code that works with these prototypes.
All right, so in order to meet our project goals, we had to set goals for code development as well. The goals for the code development were that the code should be able to use up to 8 thermocouples. It should be able to take accurate readings for those thermocouples. We decided to be within 5 degrees Celsius of the true temperature. It should be able to store 30 minutes of data without overwriting or otherwise corrupting the data. It should be simple to use, so you don't have to be engineers in order to make use of our product. The data should be easily transferable to a PC so that you can actually analyze it and make use of it. And lastly, we wanted to be sure to use open source libraries so you wouldn't have to worry about licensing or anything like that. Next slide, please. All right. For a code development process, this year we more or less started from scratch. We had inherited some code from previous years, and while that code did have a lot of features, the core functionality wasn't there. It didn't always work properly. So for this year, we decided that we were going to start from scratch. We were going to make sure that the core functionality was there and everything worked properly before moving on and adding additional features. So that's how we started with our first prototype. For that, we kept it simple. We only used 2 thermocouples. We used the delay function built into the Arduino in order to time our readings. We used the internal flash storage to store our readings during operation. And lastly, we would transfer data to the computer via a blind serial dump. By that, I mean the Arduino would not wait to see if the computer was waiting for the data. It wouldn't wait for a signal. You would flip a switch on the outside of the prototype, and it would just spit the data out. The reason for all those decisions was in order to keep our code very simple so that we could make sure, okay, it's collecting data, it's storing it properly. We're not having any issues there. Next slide, please. Thank you. Our second prototype, by this point, we had ironed out all the kinks with that basic functionality, and now we want to improve it. We want to make it more user-friendly. We also expanded up to 4 thermocouples this time. But this prototype used timer interrupts instead of the built-in busy wait function. So this allows you to do other things instead of the Arduino being stuck waiting for the next reading. We are using a micro SD card for storage instead of internal memory, which in addition to being much larger, it's also non-volatile. So if you were to turn off the device, you wouldn't lose your readings. And lastly, our Arduino is now controlled via serial communication, and it uses a text-based UI. You can see an example of a log of our console on the right. Using this console UI, you can now control the system to start and stop taking samples. You can transfer data from the system to the PC, and you can adjust the sample rate all via the console. Here is a block diagram of our system. As you can see on the far left, we read in temperatures using our thermocouples, which then output a voltage differential. The digital thermocouple amplifiers then convert this into degrees centigrade, which is then sent to the Arduino Micro. The Micro sends and receives data from the micro SD card. Whenever this is occurring, a control signal is used to light up an indicator LED just to indicate data is moving between the SD card and the Arduino. Lastly, when connected to a computer, the computer will send control signals via the serial console, and the Arduino Micro will send data in return. This is a code block diagram for our second prototype. As you can see, there are 2 main blocks here. The left one being the user interface block and the right being the data collection block. So in the system, whenever it's done initializing timers and the SD card and whatnot, it will then busy wait to receive a serial message from a computer.
It works. It should work.
Excuse me, could you please? There we go. Okay, so if it receives a serial message, it will then go into this user interface block. You saw an example on a previous slide showing what that would look like to the user. On the Arduino side, it'll receive this message and it'll parse through it and see, okay, is it one of our commands? Is it a clear command, in which case I will clear out the SD card of all data? Is it a dump command, in which case I'll print all the data to the console? Is it a set command so that I will change the sample rate? Is it a start or a stop command, which of course starts or stops taking readings? Or is it a question mark, just to print out a list of all viable commands? And if it's none of those, it'll simply say that's not a valid command. After replying to whatever message it received, it then loops back into the serial message wait loop there. Now, at any point, if the timer interrupt fires, by default that's once every second, but as I mentioned, you can change that through the console. It'll then break away and it'll check, okay, are we recording data at this time? If not, it will go back to the wait loop. But if it is, it will then break into the data collection block there. The way it collects data is by creating a string data element. It will then add a timestamp, that being the uptime of the system minus the uptime of whenever the start command was called. It will then add the temperature readings from all 4 thermocouples to the string. And lastly, it'll print that string to the SD card, specifically to a text file on that SD card. Now, that's how our system works. I'll be passing along now to Michael Kishler, who will discuss how we started testing it.
Thank you, Alex. For our test, we want to make sure that, for one, our thermocouples that we're using were actually calibrated correctly. For this, we researched industrial standards and found that an ice bath test allowed us to have a consistent 0 degrees centigrade temperature that we could then use our thermocouple to test over various time increments. From this, we could ensure the validity of our experiments and understand that we could go on to further more robust testing with an actual working thermocouple. The next type of testing we did was the junior mechanical engineers that were down with us in France helped us research various thermal barrier material. They selected various products to see which would be the most insulative for the hot environments that they were seeing. Although we did not necessarily utilize this for our version of the project, this type of technology and knowledge can be used for future iterations down the line. Now, for our next testing is actual testing inside of an oven. So this graph, you can see the blue line is the temperature inside of the oven, which is going up and down above 200 degrees Celsius. And then the red line is the temperature inside of our thermal barrier. Now, this temperature cannot exceed 50 degrees centigrade, or else it is detrimental to the actual circuitry. So this shaded region in the gray, you can see that the temperature rises as time goes on. However, this test was made without a phase change material, which is essentially just an ice pack that is used to keep the energy down, the temperature inside of the thermal barrier down without costing too much money. In the next experiment that we did, you can actually see the implementation of this phase change material. Again, the temperature of the oven is in blue, fluctuating above 200 degrees centigrade like we would see in the tunnel ovens. But this time, the temperature inside of our thermal barrier is actually decreasing from the temperature that it started with. From this experiment, we could verify that we had a working way in which we could keep the temperature environment inside the thermal barrier to a minimum. Now, our final test in France was a proof of concept of the first prototype. This was done without a phase change material. In this graph, you will see the top line, which is yellow, is the temperature of the thermocouple that it is giving us. And then we have another line below that in gray, which was vernier, which was just another way that we could check to ensure that we were getting the correct readings from our thermocouple. Although these lines are not identical, they're not on top of each other, there's a small temperature difference. However, with a simple offset, we can account for this change. Also, the no phase change material shows that the temperature begins to rise above 50 degrees centigrade. However, from our previous tests, we are sure that we can keep this temperature down with the inclusion of a phase change material. Michael Moldovan will now go on to talk about the testing we did in America, as well as some of the software work that he did.
Thank you, Michael. So when our team first moved to France, from France to the US, we had some adjustments to make some adjustments to transition to a new lab setup. As you can see on the right, this is our testing apparatus located in the senior labs at Grove City. We encountered some obstacles when we realized that some of the temperature recording instruments were inaccurate. This made it difficult to perform controlled experiments and collect valuable data. Another issue we had was while we had a thermal barrier, we lacked phase change material, which made it difficult to perform lengthy experiments out of fear of damaging our prototype with extreme heat. Finally, moving the prototype to the US caused some wires to get bumped loose, resulting in errors when testing our equipment. While these problems arose unexpectedly, our team was eventually able to overcome them and create this, another successful proof of concept test, similar to the one Michael Kishler mentioned, using the on-campus equipment in the US. This one was performed without phase change material to match the experiment performed in France. Once again, showing that with a few adjustments, we were able to pick up exactly where we left off when we returned to the States. Next slide, please. When running these tests, it was common that we'd run into obstacles after dedicating lots of time to an experiment. You can see the formats in which our first two prototypes would display data. Prototype 2's display is down at the bottom. It was common that we'd run into obstacles, while readable in the console, this format made it impossible to move data to another program quickly, as attempts would end up taking each piece of data from each category line by line. Prior to the semester, every test performed required someone from the team to manually input temperature data from each respective thermocouple by hand. This slowed down testing and limited the number of tests we were able to have time to perform. Because of this, we wanted to make testing more streamlined as possible and emphasize clean data acquisition. This led to the creation of PyParse, our own parsing program used to cut down on data acquisition time by collecting and organizing data into an Excel document. To hold to our open source claim, this was programmed in Python and uses only one non-native library. Down at the bottom here, you can see an example of the program running, as well as the Excel file created and named by the user. This program is self-contained in a folder, which has instructions for easy use and example files for new users to test the program before using their own recorded data. Next slide. This is how the data is formatted inside the Excel sheet. It neatly shows the names and timestamps, as well as the recorded data for each respective thermocouple. This program allowed us to plot and organize data very quickly and sped up the testing process to allow for additional tests with no human error. Now I'll move back to Michael Kishler and he can talk about our budget.
Thank you, Michael. Starting off here, we have our sensitivity diagram. This gives us a general layout of understanding where our funds went for the project. As you can see, a majority of the cost came from the thermocouple equipment. Knowing this, we discussed what types of thermocouples to use. There was the K-types and the T-types. We chose K-types because they were cheaper than the T-types, as well as their ability to function better in high temperature environments. We also chose to use Arduinos instead of something more powerful, such as a Raspberry Pi, because again, we don't need that high computing power and we really want to emphasize this low cost. In our next diagram, you can see how much funding actually went to each of these categories. Again, we want to keep this low. So for the thermocouple equipment, it's just $150, contributing only 28% to our total, and then $94 for the Arduinos, which brings us to about half of our budget. The rest of the equipment was just general circuitry components such as switches and batteries. And through this, we kept our total budget to a $541. Now on this slide, we can see how much money it actually costs to create both of these prototypes. Again, prototype 1, we used an Arduino Mega. It was a larger prototype, but it had its own onboard storage with the Mega. However, we went to the second prototype to slim things down. We used an Arduino Micro, which didn't have as much storage. However, we could utilize an SD card reader as well as an SD card in order to account for that memory loss. The second prototype was also closer to our design goals of 6 to 8 thermocouples, making the price go up in the thermocouple section, and also used a perf board instead of a breadboard to keep the size to a minimum, and also utilize barrel jacks for the ease of our customer. In total, the budget was $541. Some of this funding went to testing other equipment as well as the initial design for the third prototype, which Tony will now get into now.
Thank you, Michael. So as I brought you guys quickly through our first 2 prototypes and our initial proof of concept, we're looking on features for which microcontrollers to use and then for really minimizing R. But where we are currently is designing prototype 3. So moving past those 2. And with this, we're looking at a thinner but wider enclosure to better replicate our competition. Because we have a large horizontal space that we can lay out in. And if we can get our enclosure down to 3 centimeters, that would be very optimal. So prototype 3 has a 6 to 8 thermocouple design based on what the client wants with an integrated PCB. This PCB, which is a printed circuit board, allows us to horizontally arrange our circuitry components as our microcontroller, our micro SD chip, and our thermocouple amplifiers. It is the green square on the right. And then it allows us to minimize our wiring so that it's less comprehensive to put together, and it really brings in a robustness into our components. It does spread things out, however, but that is okay, since this is our largest prototype, but it is also our thinnest. And this one comes in at a roughly $230, but that is still way under the competition price. So as we closed off this semester in this project, we wanted to look back at the objectives that we had set in the beginning to see if we had met them. So develop a sensor array with a thermocouple sensor array. Each prototype did that. We did that in prototype 1, and we kept the same Arduino-based thermocouple sensor through the next 2 prototypes. Thermal testing, as in the thermal barrier that will protect this DAC unit, and the capabilities of its thermocouples to predict accurate readings. And so with a simple offset, we can get accurate readings, and our thermal barrier was designed to be with error. And to reduce the array footprint, going from prototype 1 to 2, we did that successfully. And then going from 2 to 3, we got a little bit larger, but we minimized it to 3 centimeters from that 5, which was a very important and is very valuable to our client. And the PC interface that was talked about with the PyParse program and getting the data in a very usable format for testing and analysis, that'll be implemented in prototype 3 and in our final design. So some conclusions to wrap all this up. So starting from scratch allowed us to prioritize functionality. So we took what we had from prior years, but we really started our own mini loose wire prototype so we could understand how to use the Arduinos, which ones we wanted to use, and how to get those amplifiers and K-type thermocouples working, which we eventually ended up on using our Arduino Micro with an external memory card to get the size and computing power and price that we were looking for, which this allowed us to implement features incrementally as we picked one component at a time and worked our way up and keeping budget, size, and computing power in mind. And we are the first in the history of this project to have a self-enclosed prototype. We also have 2 of them, which is really cool, and designed a 3rd, which is very helpful for us in keeping our close relationship with our friends at Onoris. And some circuitry components about this that we want to give to future project groups is that soldering connections for robustness using a PCB is really efficient for tight connections and increasing the longevity of your prototype. Open source code and open source components is really nice for versatility and adaptability. If you ever need to change it, or if someone down the line needs to work with it, they can. It's open source. It's not closed. Anyone can get access to it, which is super nice. And so from this, though, didn't come without its struggles. So problems can arise from the simplest tasks and tests. We were running our ice bath, as Kish had talked about earlier. We ran into some issues with that, and we ended up having to start from scratch with that test and research it. And then we didn't meet, some testing deadlines that we needed to meet with that. But that was okay because we kept working through that, and we kept prototyping, and we kept, solving problems as the next one arose. And then that was the solution. Was when we had a problem, we just kept working through it, kept prototyping, kept building around it, kept solving it, kept going, and eventually, we have 2 prototypes to show and a 3rd on the way, which is really cool. And it proves to be helpful in fostering the relationship with our friends at Onoris, who I want to give a big thanks to Dr. Hervé and the Onoris team, who helped us a lot in designing and giving us the specifications and requirements and showing us industry standards in the units that we were creating. I want to thank Dr. Ruber and his wife, Deb. Mark and Deb were with us in France. They were the advisors there, and they really became second parents to us. And Mark being our senior advisor in France. It was very special for us to have him there. And Dr. Rumbaugh for taking us under his wing this semester, being our advisor. It was great to work with you and to be kind of your proteges in this as you hit the ground running with us. Dr. Bright, for your guidance as well through the 4 years with this team, and coming and visiting us in France and seeing our presentation for Prototype 1, as well as Dr. Gillette for helping us build this in the lab and test in the lab and making sure that we had a firm understanding of what we were doing. Your expertise is invaluable. And also to the junior mechanical engineers who helped us with testing in France. That information is very crucial for the future of this project and building a proper thermal barrier. So thank you. I hope you enjoyed this presentation. I believe now is the time for a Q&A.
Thank you, low-cost sensor array group. If you can just keep that acknowledgement slide up, that'd be great, and that'll be our placeholder here while we go into the Q&A time. So we have a few minutes for questions. If you have a question, you can just activate your mic and give the question, or you can put that down on the text message feed. I see we have a question from Dr. Bright.
So let's say I want to add a different type of sensor, say a humidity sensor. Walk me through the changes of prototype 3 to add a different type of sensor.
So at first, going through hardware, and I'll let Alex speak to the software part of that, that we are leaving space on our PCB for future years to be able to add components, move components around. Let's say they want 6 thermocouples and 2 humidity sensors or a heat flux sensor. There's space for those to put those parts on, which allows for that versatility and adaptability. I would probably suggest initial prototyping to make sure we know how it works, and increment those functionalities part by part. But that is in the future of the project, is to add more sensors and more data collection units and different data collection units to this, to be up to industry standards rather than just a temperature probe.
A question from Dr. Brooks.
Hey guys, thanks for the presentation. It's great to hear more about your design. I did have a question for you about accuracy. Now I know some of the plots you showed, there was some difference between the external sensors you were using and your thermocouples. Could you just talk a little bit about what were the accuracy requirements? Are you concerned about that difference, or is it within the requirements?
Yeah, sure. I can talk about that. So for our design, the requirements for what the customer wanted was a 1 degree centigrade margin of error, which was exactly the results we got from our K-type thermocouple. The intent was, after we get back to America, was to create that offset and do further testings to ensure that it was exactly in line with what we were to expect. Although from the test we could see that we were very close to this required amount, and that the plan was, before the COVID epidemic hit us, to perform a test to confirm our assumptions that indeed was close enough for that 1 degree centigrade.
Thank you, Dr. Brooks. Any other questions? Follow up?
No, that's it for me. Thanks.
Okay. Molly Marino, question.
Yeah, I just was wondering what you found to be the most rewarding aspect of this project, both with working in Mont and then when you came back to the U.S.
I'm going to just repeat that question because it was breaking up on my feed a little bit. The question was, what were some of the rewarding aspects of the project? And I think what was the transition back to the U.S.? Is that correct, Molly?
Yes, that's correct. Thanks for clarifying.
Yes. Okay.
I can take that one. So for most rewarding, I would say was getting the international experience of dealing with an international client, even though there was a language barrier there between us and the Onoris team. Was just being able to encounter that and get experience from that, as that's something that not really any other team got to encounter. And then coming back to the U.S., it was a little bit of an adjustment, but I think we adapted well to our changing environment. I guess another good takeaway was just like working well, getting that team environment for an entire year, because most projects we get last only a few weeks. So I'd say that was the other beneficial part of this project.
Okay.
If you don't mind, I could add on to that. Something I found very rewarding is while we're building this, we looked into what we're supposed to make, what these things are supposed to be able to do, but to us, they're still kind of, without that application side, it's kind of just like a fancy thermometer for us. But when we produced this to Dr. Have and the Onoris team, they were blown away because they are using these things every day. And when we told them that we make this for less than $100, their eyes just lit up, and they basically told us they would take the prototype right away. It was really to be able to build something that is actually useful to the people that are trying to utilize it for their purposes.
Yes, thank you. A question from Dean Moore.
Yeah, hi. My question involves the conversion of the thermocouple voltages. There's an amplifier involved, and then I guess analog to digital conversion. Were you involved in the design of that, or was that done by a previous team? And what hardware accomplishes that task?
I can answer that one. So the hardware that we used for this task was actually a product offered by Adafruit Industries. It directly takes the inputs, or rather the output from the thermocouples, and it converts it into a digital value right there, and then communicates the temperature value digitally to the Arduino.
Follow-up question. What protocol is used digitally? Is that SPI or I2C, or how does that work?
It uses SPI.
Okay. So that was all basically, you purchased that from Adafruit, and that was then just incorporated into your design? Okay, it makes sense. Thank you.
That's correct. And that was a design decision made by a previous year, and we found it to be, well, suitable for our needs as well, so we continue to use it.
What? I haven't got my every week. That's 6.
Okay, thank you. Any other questions that just go ahead and pipe in or type in the text box there. Any questions? Any more questions?
I guess I'll ask one more follow-on question. Can you just clarify why your customer wants 6 or 8 thermocouples as opposed to just one?
I can answer this one. Oh, you can do it, Tony.
I was gonna. So the competitors normally have around 16 of them, but at the moment, ONOREIS is only using 6 to 8, and so they would like that same capability. But it's really made for the reason on the conveyor belt, and with different heats, you want to know if you have a burner out somewhere, and so those burners stretch across the whole conveyor belt and a little more, so you have to lay them out, and then sometimes conveyor belts will slow down in regions, so you want to pattern them out, the thermocouple ends, to make sure that you're getting the heat cooling sometimes in an oven that you want, black spots as they call them, or the up temperature white spots in the ovens where you need higher heat in the parts that you're getting them, and you want that, it'll show the curve of the heat, so you want to kind of correct that.
Is that it, Dr. Brooks?
Yes.
Okay. I had a brief question. Your team is kind of in a unique state of disorganization in that you started off in France and you shifted to the US, and then you had a third shift, which was shifting off campus using some of the same exact tools that you had perfected in the international setting, because you were off campus for the entire fall semester using virtual communication tools. And I was wondering if you could compare those 3 phases and how, you know, that kind of played out for your group.
Yeah, I can take that. It was very interesting, the changes that we had. Starting out in France, we all lived in the same house, so communication was super easy for us. We either lived in the same room as each other, or we lived on the floor above or below. So communication was super easy, make sure everybody's on task. And then moving to the United States, we're all in different dorms. So we had to be a little bit more intentional about using messaging, or making sure everyone shows up, and having specifically timed meetings, different times throughout the week. And then moving into a situation where everyone had to go home, just sticking to those meeting times that we had throughout the week, meeting on Teams, using those, and then continue using those messaging services to contact between the different team members and our advisor as well, to make sure that we got done what we needed to.
So how did that compare? In other words, being in France, then you're back in the States, and then of course you're off campus now. Being off campus now, is it similar or different to the time you're off campus in France?
I would say it's different because of the fact that, as I said before, when we were in France, we were all right there together. We had all our components and stuff there. So communication and working was easy. And then being at home now, we have one team member that has our second prototype. But other than that, like, we weren't able to fabricate anymore because we don't have the tools like we did either in France or at Grove City to continue that process. And also communication, as I said before, is definitely more difficult too, because all you can do is send a message or expect people to show up at a meeting instead of being able to go down in their room and grab them. So,
yeah, that makes sense. And that's a very good point. I hadn't thought about that. You were actually living all together. So that's a big difference. We have time for one last question. Any final questions? Okay. If not, thank you.